Hello. Oh yeah, I'm going to do a couple of examples from section 1.6, and I think you'll find section 1.6 perhaps to be relatively challenging slash frustrating if you're not familiar with these techniques. So I'll try to make this as clear as possible. When you do these types of problems, you have to sort of look for the form of the problems and search for these different types of special forms for first order equations. So I'm going to start off by doing this one here, 1.6 number 5. So I'll write down a differential equation. Okay, here we go. So it's x times x plus y times y prime is equal to y x minus y. Okay, and I'm going to try to see what type of a form this is. So what I'm going to do here, I'll just solve for y prime and see what we have here. So y prime is equal to, so we get y over x, right? And I'll write this very suggestively here. We get x minus y divided by x plus y. Okay, so now if you don't have experience solving these equations, you shouldn't expect that you're going to see these things immediately. But we're in this section of the book that talks about homogeneous equations and separable and all of these Bernoulli equations. So you have to kind of think about what is sort of jumping out at you. And I'm seeing this y over x. So what I'm going to do is I'm going to actually sort of multiply the right-hand side of this expression by the following: 1 over x divided by 1 over x. Just watch what happens. So we get y prime then would be equal to, so this stays the same, right? And then what I'm going to do is use the sort of the distributive law in here, in the numerator and the denominator. So this becomes 1 minus, and then you get y over x. Then here you get 1 plus y over x. And now what you see is you're looking at a homogeneous differential equation, so we can make this substitution and then go from there. So the substitution that works in this case is, if I set v, I like to use v for some reason, v is equal to y over x. Okay. Now if you make that substitution, now I'm going to solve for y. That says that y is v times x. And calculating the derivative of y with respect to x, we have that v prime is equal to v times the derivative of x with respect to x, which is 1, plus, then we just get x times v prime. Okay, now we can use these three equations here to change the form of the differential equation. I'll call it star that we're considering. So doing that, let's see. I'll just do it. So you get x v prime plus v, that's y prime, right, is equal to, and then we get v, and then we get 1. Let's see, what is it? Oh yeah, minus v, all divided by 1 plus v. All right, so now we're looking at a differential equation in the variable v, all right, and x. So what I'm going to do is basically I'll either solve for v prime or just do some simplification and see if I notice something. Okay, so what you see here is that vx prime, okay, is equal to, all right, I'm just going to do this. If I subtract v from both sides, and then if I find a common denominator, okay, and add them, what you see using algebra is you will get minus 2 v squared divided by 1 plus v. Now I recommend that you do this for practice because you'll have to do something similar to this on an exam. So just go through the algebra, subtract v, find a common denominator, add them together, and you'll notice that you get this right here. Now this thing turns out to be separable. That is, I can do the following. I'm going to rewrite v prime as just dv dx. That's what it is. Okay. And then just work this out. Okay. So if I get things in the proper form, I will see the following. I can rewrite this as, let's see here. Okay, I'm going to do it this way. 1 plus v divided by v squared dv is equal to a minus 2 dx, and then this all has to be divided by x. So now what we can do is we can integrate both sides. So I'll just do that. So the integral of this with respect to v must agree with the integral of this with respect to x. So what do we get here? Okay, so this is not too bad. We get, let's see, I guess we get minus v to the minus 1. Because I can, well, here, let me rewrite this. This will drive some of you insane, I think, if I don't do this. Okay, so what you want to do, this isn't so bad. There's a lot of very complicated integrals running around out there, but this one's not bad. See, because you can write this as 1 over v squared plus 1 over v, right, dv. And this one I'll just take care of right here. This is minus 2 times the natural log absolute value of x plus a constant. Okay. Now on this on the right hand side here, I mean the left hand side, sorry, what we have is this is minus v to the minus 1 plus the natural logarithm, the absolute value of v. So these two must agree. Now what we'll do is we will go back and trace our way back to our original problem involving y. So I'm going to just back up here a little bit. You see, when we solved this, we made the substitution, where is it? Right here. We know that v is equal to y over x. Okay, so let's use that. So v is equal to y over x, so I get minus, now it's x over y because of the minus 1, okay, plus the natural logarithm of the absolute value of y over x has to be equal to, well here, minus 2 times the natural logarithm of the absolute value of x plus c, some constant. All right, now let's see. If you simplify this, what we can see is we get the following. We get that. I'll just write this way. Minus x over y plus, now bringing this, adding 2 times the logarithm of x to both sides, we get, well here I'll just write it out. So we get the logarithm of absolute value of y divided by x plus 2 times the logarithm absolute value of x is equal to this constant. And then we finally get, this is maybe the best looking solution we can find. So using the properties of the logarithms, we see that what's left over. See this bit here, this is actually the logarithm of the absolute value of x squared. So then I can combine those to get that this is actually the absolute value logarithm of y times the logarithm of x. It's a good exercise to see why that's the case. And that has to be equal to a constant. Okay, so that's number 6 there. Or number what? Number 5. Okay, so here's another one. This is from the same section, and this is very similar to your homework. It's so similar, I'm going to call it 1.6, number 24 star. In other words, it's essentially your homework problem with a number changed in it. But I want you to see the technique, because sometimes just the actual algebraic manipulations can be made very, very annoying if you don't do them in the right order. That's what I'm trying to illustrate here, I guess. So here's the question. We would like to solve this differential equation. Okay. And here's the differential equation. 4 x y prime plus 3 y cubed e to the minus 2x is equal to 5x y. Okay, so here it is, right? Now, keeping in mind that you should feel very natural with the idea that you have no idea what to do, right? Because this is the first time you've seen perhaps this technique. You might look at this and say, oh, I've got these Bernoulli equations floating around. I have these, exact equations. I have these homogeneous things. What can I do with this? All right. So just be patient when you're working on these and realize that sometimes things will work out. Actually, what I noticed I wanted to do here to make my life a little easier, in fact, I want to change this number right here. I don't want there to be a 5 there. I would prefer, for demonstration purposes, if this were a 4. Okay, so I'll make it into a 4. Okay, so the first thing I'm going to do is divide by this 4x. So I see I have y prime, right, plus, then I get 3 y cubed e to the minus 2x divided by 4x. This is equal to y. All right, so this is looking actually, this may not look promising, but if you work with Bernoulli equation continuously, you would be very happy when you saw this, because you could then rewrite this in the following way. Y prime minus y then is equal to, minus 3 y cubed e to the minus 2x over 4x. All right, now this is looking good. If you look at what the form of a Bernoulli equation is, you'll see that this fits it perfectly. And the technique that will work in this case is if we make the substitution v is equal to, it's actually y to the minus 2 power. Okay? So now, what we're going to do is we're going to transform this equation, this differential equation, into a differential equation in terms of v using the substitution. So this requires us to find, for example, y prime. So let's do that. So based upon this substitution, we see that dv dx is, well, let's see, it's by the chain rule, it's minus 2y, right, to the minus 3 power times dy dx. Okay? Now, okay, that's great, because now I can solve for dy dx. And I guess I'll put it right down here. So then, dy dx, then, okay, what is it here? I guess it's going to be, I'll write it this way. So I have to solve this equation, I have to divide by negative 1/2, and then I have to multiply by y cubed and then I get a, yeah, oh, it looks weird because it's all on the other side as well. So we get this. Okay, so we have found our y prime, which is this dy dx. Now the key to keeping this simple is sort of leave y alone for now. Just if you just sort of let it sit there and let the y sort of come along for the ride for a while, you'll see it'll work out very nicely. What I mean by that is let's simply write down what we get when we use these substitutions for dy dx and leave the y there. Okay, so here we go. So what you get if you take our equation, let's call this star again. I guess I'm supposed to call it double star, but we're in a new problem. Take our equation star and you make those substitutions. What you get is this. You get minus 1/2, so this is what we just calculated. Y cubed, and we get this dv dx minus y, I'm just leaving that alone, is equal to a minus y cubed e to the minus 2x. It's divided by 4x. Okay, so now let's see what happens. I want to actually multiply by, I want to get rid of this thing. So it's going to be negative 2 times y to the negative 3rd power. If I do that, I get dv. When I say multiply, I mean obviously both sides of this equation by this. Okay, and I get plus 2, and now I get y to the minus 2 power. Okay, and that's equal to e to the minus 2x divided by 2x. I recommend, well, I guess, is it really 2x? Let's see. Yes. Yes. Okay. I think I did that right. What I'm thinking I'm doing, let's take a look. So I multiplied the first term here. I tried to get rid of this coefficient. See, I'm trying to get it into the form of a nice linear differential equation here in V. So I want to get rid of this coefficient right here, right? That whole thing. So I multiply by its inverse, I guess. And that would then turn, the 2 would go here, the minus sign goes away. Yeah, I believe I did that correctly. Okay. But now look, it worked out very nicely because look, V is equal to y to the negative 2 power. So then we get, as it would always turn out, dv dx plus 2v is equal to e to the minus 2x divided by 2x. Okay, so this is set up perfectly, so we can now solve this using our integrating factor. All right, so I'll do that again for review. So we want to integrate, right? In this case, I'll just integrate from 0 to x. I guess I should be careful, but I'm all right. Let's just go from 0 to x. It doesn't matter. 2t dt, right? And then what you see you get here is you get this is just oh, sorry, I'm haste makes waste here. Just the coefficient I integrate, so I get 2x possibly. Oops. Okay, 2x. All right. Now the reason for that I do that is that now I want to exponentiate that. So if I exponentiate 2x, I get e to the 2x. Okay. And now what I will do is I'm going to multiply both sides of this differential equation here by e to the 2x, and I'll see what I get. Well, I get the following here. I get e to the 2x dv dx plus, I have my 2v e to the 2x, and that's just now equal to 1 over 2x. So as it always works out, if the form of the differential equation as it was, we get the following. what you're looking at here is the derivative of the function v times e to the 2x. You can see that that has to be equal to 1 over 2x. If you look at it, right here we have, of course, that's e to the 2x right here, times the derivative of v with respect to x right here. And that's equal to, well, if you differentiate e to the 2x, you get 2 e to the 2x times v. So that truly is up there, up here, this is the derivative of that. And that's what we're looking for, because now we can anti-differentiate both sides with respect to x, and we get v times e to the 2x is the indefinite integral of 1 over 2x dx. So we obtain the solution to this differential equation in terms of v as follows. V times e to the 2x is equal to 1/2 the natural logarithm of the absolute value of x plus some constant. Okay, now we have to, let's solve this again for v. So v is equal to, here, I'll just write it this way. It's e to the negative 2x times 1/2 times the log of the absolute value of x plus a constant. And now we must try to trace our way back to our variable y. And here we see that v is actually y to the negative 2nd power. So there we go. So we see that y to the negative 2 power is equal to e to the minus 2 over x times 1/2 the natural logarithm of the absolute value of x plus a constant. Now taking the, I guess raising this to the negative 1/2 power, we see that we get y is equal to e to the x, right, see how that, right, by the exponent laws, times 1/2 natural logarithm absolute value of x plus c to the negative 1/2. Okay, so I hope this helps, and so just finish off your homework and make sure that you try to become comfortable with these techniques. It will take some work. It's not the kind of thing that you can sort of just watch. You want to make sure you do your homework and maybe pick out a couple of problems, search the internet, do something. So if you have any questions, please contact me, and I'll talk to you later.